welcome back to the shop. Right now we're engraving the dial for the cross slide of my lathe. And I have my Vertex rotary table with the dividing attachment, with the dividing disc mounted on the table. I have up here a template which just gives a straight motion when I move the stylus through it to cut the lines. And I have a pyramid shaped cutter in the spindle, which I will show later because they are pretty neat and very easy to make and very robust. And I have 200 lines to engrave, and then the longer ones and then the even longer ones. And right now we cut 200 lines all to the same length. I have a 20-hole dividing disc, and I have to go 9 holes each time to get my 1.8 degree division. Okay, right now we are engraving the numbers, and of course you see that this is a round surface. We're engraving on a curvature, and that means that the depth of our engraving changes all the time. We could set up the pattern plate to make the machine follow the curve automatically. But as it's only a few numbers, I'm going to do it manually. That means while I do the engraving, I'm feeding in and out with the fine feed up here to compensate for the curvature. That takes some exercise, but once you get it, the results are okay. It's not the best practice, but it's pretty fast. So I put some red edding. That's that's what we have instead of a Sharpie on there, so the engraving is more visible. And yeah, we're good to go. I just lowered the table slightly, and we're good to go. Oops. Okay, let's take a look. Doesn't look too bad at first look. It's always a bit hard to judge the depth of an engraving, but there is a trick to it. You just use the soft eraser out of the art store, and you press it onto the engraving, then you lift it off, then you get an imprint of your engraving. Yeah, it should be pretty good visible on camera. Down here are the lines of the graduation, and up here is the number. Of course it's mirrored because it's imprint. But from that we can judge that depth of our engraving is pretty much the same as the depth of the engraving of the lines, and that's what we want. So, one done. Let's turn the dividing head to the next number. Should be right here. There we go. The manual adjustment on the engraving depth is a bit touch and go, or touch and feel. And we need to go a bit deeper because the imprint is very shallow. This soft eraser. It's also nice to pick out dirt out of knurling, engraving, fine threads, to pick up dirt from the screw head, insert screws from tool holders when you don't want to use compressed air. This is widely used in clockmakers, watchmakers use this a lot to clean up little particles of dirt. And also the CNC guys that have optical tool presetters use this to get the fuzz off the tip of the tool before they can measure them with the optic, with the magnifying, with the microscope. So it's really handy to keep around, and as I said, you can get this in every art store for a few bucks, and it lasts very long. With the time they get a bit grumpy and ugly with all the dirt they collect over the time, but they still work. So okay, this is the finished tile, and now we can disengage the worm drive and can take a closer look. The lines are better visible here because I blackened them up with some Sharpie or edding and cleaned off the excess. But yeah, you see that it's going all around. We get a nice even pattern. The numbers are starting at 0, and we raise by 0.5 millimeters. 1, 1.5, 2, 2.5, 3, 3.5, and go back to 0. That means we have 4 millimeter in diameter each turn with this tile, and each line, as we have 200 lines, is 0.02 millimeters in diameter. Okay, there was a little leap forward in time, and I got the crank finished. I machined the crank and the handle from solid, and I will show you some pictures where I turned the crank with the 3 balls using my ball turner. First I rough turned the shape with a parting tool, then I set up my ball turner, which I will do a separate video on, because I never showed this actual on camera, to machine the balls. And yeah, then I parted it off. I finished the ends with file and emery paper, and then I machined the central bore, and the crank was done. It's just locked in place with a single set screw, and I filed the flat onto the feed screw. Then I machined the handle, and I freehand turned it. I use it's like wood turning. You have a handheld tool, and you machine it by hand. And there will also maybe a separate video on this topic, because it's quite a nice process, and you, if you would turn this without a tracer attachment or a CNC lathe, this would take quite some time if you don't graver turn it. So, and I also made this little thumb screw, which locks the dial. So you loosen this screw, you turn the dial to whatever number you need, maybe 0 for example, and then you just give it snug it up lightly, and you're good to go. Oops, kicked the tripod. And it really feels quite nice with the tool ball, with the two angular contact bearings in there. It really feels like yeah, like it should. And even if the design of this crank is not the traditional one, where one of the balls is bigger than the other, I quite like it. It looks nice, and I had to make sure that it doesn't interfere with the crank of the bed slide, so they don't hit each other. And you can crank it with one hand very fast, and you can very precisely advance it, and you can also hand over hand advance it for facing, like you do. Yeah, that's the crank. Now we need to engrave the vernier, and it will only be a very simple vernier. I want a 0, and I want a mark for 1/100th of a millimeter advances. Okay, this is how the vernier will look. We need one line that's a 0, and a second line that's exactly between two of the lines. It doesn't matter which line we are between, they only have to be between two lines. And I just offset it by 5 lines and went back half a division. That's 9 degrees minus 0.9 degrees, so we have 0 and 8.1 degree. And yeah, that's our vernier, 0 and 0.01 millimeter in diameter. I'm used to lathes that show the actual diameter on the dial and not the distance they travel. I don't see it. For me, it doesn't make very much sense to have a dial that shows the travel on the lathe, because you're measuring diameter and not the radii. So yeah, that's why I go for diameter dials. Okay, we're at the engraving machine, and I set up the small dactyl dividing head or rotary table. Yes, that's the rotary table we made the chuck jaws for. First project ever on this channel. No need for the big indexing setup on the vertex rotary table, because we're just engraving 2 lines. This don't get distracted by this. This is just some white paper to bounce some light back onto the workpiece so you see something. I'm running the same pyramid-shaped engraving bit, and yeah, I set up a template that gives me a straight motion, like this, a line. Then we will index 8.1 degree and do the second line. So let's go, let's zoom in and have a go. Okay, and I'm just engraving a 0 mark there. A 0. Okay, let's see how this engraving came out. Okay. Yeah, you can see, it's hard to see, here in the reflection you can see the 0 engraving, the imprint from the engraving. That's all we wanted. And now we're good to go. Now we can take this out of the chuck and see if it fits. This is how the vernier ring looks on the lathe. We have our 0 mark here and the vernier line for 1/100th of a millimeter diameter reduction here. And to use it, it's very simple. You touch off. It's like you would work on a regular lathe or mill. You touch off, you set it to 0. And now let's say you want to reduce the diameter by 0.51 millimeter. You go to 0.5, and now you need 1/100th of a millimeter more. The divisions are 0.02 millimeters, so you want to go in half a division, and that's when you use the right index line. So you line the right line of the vernier up with the next line on the dial. So now you have 0.51 millimeters in diameter. And that's of course for all possible combinations. And now we can check the accuracy of this dial. Okay. You see now 2 pictures. Up here you see a dial test indicator which monitors the movement of the cross slide, and down here you see the actual dial of the cross slide. This is set to 0, and up here we are at the even number at 20. So we feed in on the dial 0.1 millimeter in diameter, so this should move 0.05 of a millimeter. So let's go. Let's see what the dial shows. Exactly 0.05 millimeters. Let's go 1/100th of a millimeter in diameter more. and the dial test indicator shows half a hundredths, that's 5,000ths of a millimeter actual movement, and that's half of 1/100th of a millimeter. And when we go back to 0, move back, get the backlash out, go back to 0, the dial test indicator also goes back to 0. So this seems to be pretty precise. When we dial in 0.02 millimeters on the diameter, like this, we get pretty exactly 0.01 millimeter movement on the dial test indicator. So I'm very happy how good this dial is. Let's go. I can't monitor bigger movements because of the dial test indicator has only 0.3 or 0.4 millimeters of travel. But we can go in 0.2, and this shows 0.1 up here. 0.3 millimeter in diameter, this should show 0.105. 0.15, yes. And if we go half a division on, we also move 5,000ths of a millimeter up on the dial indicator on. So I'm pretty happy how this came out. Okay, yeah. I think we stop here. The vernier ring only needs a locking screw, but I won't show that on camera because I'm just going to drill and tap a hole on its diameter and machine a brass screw to clamp it. And apart from that, we're done. I'm very happy how this came out, and this is a great improvement on my Chinese lathe, which isn't Chinese anymore. The only drawback to this modification is now I have to do the top slide and the bed slide crank too, because you see that there is quite a lot of backlash, and also this hand wheel is kind of crappy. I don't like this very much. On the bed slide I want a disc type crank, but I want it to be steel and solid. Also to have some inertia when you crank it. And I want to get rid of the backlash. Yeah, so that's it for now. Thank you for watching. See you next time.